regarding set theory is Cartesian products and sequences, which surprisingly are the same topic. To prepare for that next video, here we need to establish the basic rules of what might be called set arithmetic, adding together and intersecting sets. Set theory is not easy to define. We run into logical conundrums all over the place that require some careful thinking, and some decisions about how we want to proceed need to be made. It's all very interesting, so stay tuned. Okay, so the union of sets and the meaning of the word or. The union of A and B is denoted by this, A union B. Union means every element that is in A or B. So formally, union is defined by... So it's interesting how similar mathematical language is to the language of programming. So, because here, the meaning of or is a little confusing in math and in programming. In programming, or means either one or the other or both. And then in programming, if you want to say either one or the other but not both, there's a separate operator for that, an exclusive or. Okay? Math doesn't really have an exclusive or, and it makes the or a little bit ambiguous. So if this means one or the other or both. If you want to say one or the other but not both, you need to actually just say that explicitly with words. Either this or that, but not both. So X may very well be in both A and B, and in fact, that's the way we would picture the union as two overlapping circles, and then the union is everything in either one. So the intersection, and then also the meaning of if-then. So the intersection of AB is denoted by the upside-down union, and the intersection is every element that is common to both sets. So formally, we define it as X such that X is an element of A and X is an element of B. It's interesting, this seems simple, but there are complications popping up already. In order for this to make sense, we need to have another convention, the empty set, which we denote by this, which we think of as a set having no elements. So that if A and B have no elements in common, we would say that A intersect B equals the empty set. So in Venn diagrams, it would be like this, right? They have no sets in common, no elements in common. We also express this fact by saying that A and B are disjoint. Now, an interesting point about the empty set is that it's merely a convention. You may very well ask,
I am asking.
And will you make?
How can a set of objects have no objects? And it's just a shorthand that makes dealing with sets easier. It's kind of like the fact that infinity isn't actually a number, it's just a convention. So we need to define other conventions relating to the empty set. So for every object X, X is not an element of the empty set. That's kind of obvious. And regarding union and intersection, the union of A with the empty set equals A. The intersection of A with the empty set equals the empty set. Those are obvious. But the inclusion relation is a little more tricky. What about this? Is the empty set a subset of A? Well, this is a shorthand way of writing the sentence, every element that belongs to the empty set also belongs to the set A. Is that statement true or not? Every element that belongs to the empty set also belongs to A. So there's a new concept here. So look at this statement. If x squared is less than 0, then x equals 23. In this situation, x squared is never less than 0. So it's irrelevant what the conclusion is. A statement of this sort is said to be vacuously true. A lawyer might call it nugatory. The statement might be true, but it's trivial and weightless. Okay, so what about this? We can see that given what we just said, the empty set is a subset of A does hold for every set A. Because writing this is the same thing as saying that if X is an element of the empty set, then X is an element of A. And this statement is vacuously true, same as here, because it's never true. No element X is an element of the empty set. So what all of this is saying is that there are some issues that we cannot resolve by argument. You can't make a better argument that this is true than that it's not true. And instead, we have to just agree on what we mean. So mathematicians have decided that yes, the empty set is a subset of A. That just makes all of our work easier. Okay. So next up is the difference of two sets. We use the difference of sets frequently in topology. So the difference of two sets is denoted by this. Some authors say A minus B, but there's some confusion about that because sometimes that means take every element of A and subtract every element of B. So this just makes it clear we're talking about the difference of the sets. And it's defined as the set consisting of the elements of A that are not in B. So here formally, this is sometimes called the complement of B relative to A, or the complement of B in A. Complements of sets are very important in topology. When the context is clear, the complement of a set can be written with a hash mark. So if we're talking about a set of rational numbers, so if our context is rational numbers and we have a set of rational numbers, then we can just write the complement of B as B hash mark, which means all of the rational numbers that are not in B. So those are our three operations. Whoops. A union B is everything. A intersect B is just the middle. And if this is A and this is B, then A minus B is just all of this. And then there's a couple more possibilities here, because this one is not commutative. So we also have B minus A, which would be all of this. And then there's actually one more here, which would be everything that's in one of the sets but not in both, just to make it complete. And there's no real operation for that, but we can write it down as A union B minus A intersect B, right? So we'd start with the union, and then this part is the intersection, so we're taking the union and then taking out the intersection, and we'd end up with that. So this isn't really an operation, but just it's sort of the one thing that we don't have an operation for. Okay, the rules of set theory. So intersection distributes over the union. So if we have three overlapping circles, B union C is everything here. And then A intersected with that is just this part, right? And if we do it again, A intersecting with B is just this part, and A intersection with C is this part. So the union of these two would be this, so it's the same. We end up with this part, we end up with that part. Okay, that was easy. Interestingly, union also distributes over the intersection. So it's kind of weird that each operation is distributive over the other one, but it's easy to remember because it works both ways. Let's just test it real quick. So we have B intersects C, that's this one, and then A union with that. So it's all of A plus this little tail, right? And then this one is, we have A union B and A union C. And then we take the intersection, and what do we end up with? We have A with the little tail. So they're the same. Interesting. Now we also have De Morgan's laws. These are super important, and we will be using them frequently. Verbally, these just say that the complement of the union equals the intersection of the complements, and the complement of the intersection equals the union of the complements. And if we think of set difference as complement and we understand the enclosing set, then we can also just write these as Okay. So let's prove one of these, and the other one will be similar. So one is the complement of the union equals the intersection of the complements. So let's let P equal the left side and Q equal the right side. So as always, and as we did over and over when we were proving the uniqueness of the real numbers, to prove set equality, you prove inclusion in both ways. So first we have to prove that any element of P is also in Q. Then we prove that any element of Q is also in P. That means that the two sets are equal. Okay, so first, let X be an arbitrary element of P. So that implies that it is an element of this. That implies that it is an element of A and not an element of B union C. That's the definition of difference. That implies that it's an element of A. If X is not an element of B union C, it means that X is not an element of B and that X is not an element of C. And then if X is an element of A and not an element of B, that implies that X is an element of A minus B. And if X is an element of A and not an element of C, that implies that X is an element of A minus C. And that implies that this is just the definition of intersection, right? If X is an element of this set and it's an element of that set, then it's an element of the intersection of the two sets. And this is the definition of Q. Therefore, P is a subset of Q. Okay, B. Going the other way, let Y be an arbitrary element of Q. And then we just do the same thing. We just apply the definitions over and over. So that this means that X is an element of each one of these sets. This means that X is an element of A but not an element of B. Then again, X is an element of A but not an element of C. And then if X is not an element of B and it's not an element of C, then it's not an element of the union of B and C. So we have that X is an element of A, but X is not an element of B union C. And if X is an element of A, but it's not an element of this set, that means that X is an element of A minus B union C. And that is the definition of P. Therefore, Q is a subset of P. P is a subset of Q, Q subset of P implies that P equals Q. Okay, easy. And number two, that the complement of the intersection equals the union of the complements can be proven in the same way, just following the definitions. Okay, now things get more interesting. Collections of sets. So the objects belonging to a set can be anything. That means that the objects belonging to a set may themselves be sets. So we now have another way to form new sets from old ones. So given a set A, we consider sets whose elements are subsets of A. In particular, we can consider the set of all of the subsets of A. And this is sometimes denoted this way, and it's called the power set of A. And it's called the power set because if A has n elements, then the power set has 2 to the n elements, including the empty set and the set A itself. So we can just test that with a couple of examples. The empty set has 2 to the 0, right? There's no elements in it, and that equals 1. So the power set has 1, namely the empty set. So remember, the power set is every subset of A, including the empty set and the set itself. A set with 1 element has 2 to the 1 equals 2, and what are the subsets of this? It's just 0 and the whole set, right? So that's right. Now, what if we have a set with 2 elements? Then the subsets would be the empty set, the whole set, and also 2 subsets, one for each one, a subset for each one. So there's 4 of them. So it works. If you did another one, you'd see that it's the same thing, and so on. So when we have a set whose elements are sets, we usually call this a collection of sets, and we denote these by scripts, which are kind of hard to write. I don't know, fancy versions of regular letters. Okay, so this will help us keep things straight. in arguments where we have to consider objects and sets of objects, and then also collections of sets of objects at the same time. And this is what topology is all about, so this is important. So we have to be a little bit careful here because we need to make a distinction between the object A, which is an element of the set A, and the one element set A, which is a subset of A. So if the set equals ABC, then these statements are all true. So the object A is an element of the set A. The set with one object A is a subset of the set A. And the set with one element A is an element of the power set A, because this is a collection of sets. These statements are not true. The set with the element A is not an element of A. The element A is not a subset of A. And the set with an element A is not a subset of the power set, because this is an element of the power set. It's not a subset, okay? So we have to be very careful to keep these concepts straight. Okay, so arbitrary unions and intersections. We've already defined what we mean by the union and the intersection of two sets, but there's no reason to limit ourselves to just two sets. We can just as well form the union and intersection of arbitrarily many sets. So given a collection A of sets, the union of the elements of the collection is defined by the equation: the union of all the sets in the collection is the set of all x such that x is an element of at least one of the sets in that collection. Okay, and then the intersection is defined the same way. Okay, so this just means you take all the sets and take all the elements of every set. This means it's only the elements that are in every one of them. Okay, that's pretty easy. There's no problem with these definitions if one of the elements of the collection happens to be the empty set. That's okay, because if one of these sets is the empty set, that doesn't do anything to the union, because it would still just be all the elements of all the sets inside the collection. And if the empty set is one of the sets in the collection, then the intersection would be the empty set, because there's one of the sets that doesn't have any elements, right? That part is easy. But what does it mean, if anything, if we allow A itself to be the empty set? In other words, it's a collection of sets with no members. What does that mean? So if we apply the definitions literally, we see that no element x is going to satisfy this criterion, because there are no sets inside the collection for x to be a member of. So it's reasonable to say that the union of all of the sets in the collection is the empty set, because there's nothing in it. But on the other hand, the intersection isn't as easy, because every x satisfies this criterion, because every x that you can come up with is, in fact, in, quote, every element of the collection, because there are none. So this, again, is vacuously true. So what do we make of this? What do we mean by every x? The question is, every x in what set? We're getting back to what we talked about last time, about the context of our discussion. What is the enclosing set from which we're taking objects? When we say every x, we don't mean every x, surely, right? What about my car, or this video, or my phone? Are those in the set? Probably not. If we have specified the larger set capital X that is the context of the discussion, say rational numbers or positive reals, then it would be reasonable to let the intersection of an empty collection be all of the larger set capital X. Some mathematicians think this is okay and define the intersection of the sets in an empty collection to be all of the enclosing set. But not all mathematicians follow this convention because of this inherent ambiguity. To avoid difficulty, we're going to leave the intersection of sets in an empty collection undefined. Okay, that's enough for this week. After this, things get really abstract and obscure. We're going to talk about one more way of forming new sets from old ones, which are Cartesian products. These are obviously foundation of basically all of math, right? And defining them starting from a foundation of set theory is very involved, and so we'll do that next time. Thank you. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.